Morning, guys.
Good morning. Hello. Good morning.
Good morning. Let me turn this music off. Where is it?
Hello.
Hi. It's 10:30. Okay. Let me finish typing this in. So I didn't get the slides on to iLearn for before lecture. I can do that right now if people need that for note taking, or I can do it afterwards if you don't need it immediately. So if you do need it, speak up, please. Okay. We are going to go through a lot of different things today, and so I'm trying to get everything in an order that is going to make the most sense to everybody. We're only going to get partway through today anyhow, because there's so much to cover when it comes to faults and earthquakes, especially living where we do, right? It's important that we talk about this in pretty good detail.
Are we going to be able to go over questions about the other lab?
Sure. Like what lab? You should probably tell me which one you mean.
Or the first one, pre-lab?
Sure, yeah. Yeah, would you go for it? Ask me a question.
Something is not working for me. I would have been finished already, but
What's not working?
the topographs part.
You mean the layer that you're supposed to insert into Google Earth?
Yes.
Okay. So let's go look at that.
I tried it on both my phone and my cell phone. I mean, my computer and my cell phone.
It's
And
not going to work on your cell phone.
yeah, I tried it on my computer and it didn't first, and then it didn't work.
Okay. So, let me share my screen here. I've got Google Earth open.
But it was
Okay.
easy for me to get all the previous information before that.
So, okay. So you got Google Earth running on your computer, no problem, right? And
It doesn't
you
look like that on my computer.
downloaded the app. You're not using the website, correct?
Yes.
Okay. So if you look at my screen, ignore all this stuff. I've got like a ton of different layers.
Kind of different on my computer.
It looks different.
Yes, because it's downloaded.
This is downloaded.
It's kind of confusing the way my app is.
Okay. So it
Sidebar.
should open up. I mean, you should have, it's like a globe symbol that is the app, and you just double click on that to get it going, and then you're gonna, so it's gonna look like this. You're gonna have Google Earth Pro here. You're running the app, and then within that you're gonna go to File and then Open, and then navigate. I don't have anything in downloads right now, but you would have these two layers over here. So there's the geologic units of California. That was the cagl.kmz file. And then there's this Earth Point topo map layer. So both of those, let me switch over to.
Yeah, mine's is not, it's a little different. It's not really.
Okay, let's do step by step. So
I didn't download it. Maybe that's the problem.
you haven't downloaded it? Okay, well, let me take you through a couple more steps, and then let's see if we can solve this problem. Okay, so here's iLearn. You need to go to lab. Oh, I didn't mean to click on that just yet. You need to go to lab 5. It's in our current week. So click on that. And then up at the top, this is for the pre-lab 5A. These are your worksheets. And then you need to download this one, number 2, Geologic Map of California. And then number 3, Earth Point Topo Map, this file. Those are going to go to wherever your downloads go to. If it's your download folder, you send them to your desktop, wherever they go. So let's see, I can just do that as an example. I'll download this. So it shows no preview available. It just goes to the download.
Oh, I see.
Then
So
I'm
my,
going to go back. I'll click on, oh, did I already get that one? I did. I didn't mean to do that.
my computer is saying that this app is only available on App Store, on the Apple Store for iPhone and iPad because I have a MacBook.
You have a MacBook. Well, I'm running on an iMac, not an iMac, a
No,
MacBook Pro.
it's not letting me download it. It allows me to use the app, but it does not allow
Okay.
me
So
to.
I wonder whether you have like a pop-up blocker or something else going on.
I think
Um,
so because it won't let me purchase it. It's saying only for the iPad or the
well, there's
iPhone.
no purchase. You don't need to purchase
I
anything.
mean, download. It won't let me download anything.
Okay. So are you going to, wait, where is it? So where did I have you download Google Earth? Wait, where's that instruction?
In the
Da, da,
beginning.
da. Oh, that's right. I put it up here. That's right. So you must download Google Earth. Click on Google Earth Pro on desktop. So this, click on this link,
Let me
and
try.
that will take you, that will automatically download the right app for you. So you just accept and download. So I would try that again. If you click on the other link, you get this page where it says Google Earth on the web. You don't want that. Google Earth on mobile. You don't want that. You want Google Earth Pro on desktop, even if it's a laptop, right? So click on that and that'll take you to the same place I just showed you. Basically,
Where does
you're
that
down,
say?
huh?
Where is that located?
So go to the Lab 5 folder, and right up at the top in red, it says you must download Google Earth to your computer. Click on Google Earth Pro on desktop. So if you click on the second link, it'll automatically try to download it for you. If you click on the first link, it'll take you to this, and then you just want this right-hand option, Google Earth Pro on desktop. Then you download that.
Wait, say it
So
again. Sorry, I'm just.
it's okay. Are you writing this down?
No, I'm going there right now.
You're doing it. Okay, so where are you? Why don't you tell me where you are?
Well, I'm on the where it shows all the files for it.
Right here in iLearn?
Yes.
Okay, so go up to the top where it's in red and click on where it says click on Google Earth Pro on desktop. Click on that link right there. It's above where it says Lab 5A pre-lab. It's above that in red type.
Oh, it just says must download Google Pro to your computer.
Okay, and then in the next line, it says click on Google Earth Pro. Click on that. Click on Google Earth Pro on desktop.
It doesn't say that here.
Do you need to refresh do you want to share do you want to share your screen so I can help you that way?
How do that? How do I do that?
Okay, so you should be able to, okay, now I've given you permission. So you
Oh, I
should be
think I can.
awesome. Okay. So put your pointer up at the top where it says you must download Google Earth. Okay.
Oh, right here.
Go,
Oh,
yeah, click that.
sorry, I'm a little wrong.
And then you're good. Accept and download. Now it's downloading. So give it a second to download for you. Did you download the other two files? We can go back and do that too.
Which one?
So go back to the lab folder in iLearn. I think if you just go your second tab, maybe Lab 5A. Oh, okay, maybe the left-hand tab then. The one all the way on the left where it says Google Earth or Earth. Okay, your furthest left tab. This one over on the, yeah, keep going. Keep going. That, yeah, click there. Now do the back arrow. Okay, now you need number 2 and 3 also. So number 2, yeah, click on that, download that one. Download that. Okay, now go back again Let that download. Okay, yeah, click on the first tab, go backwards again, and then click on number 3 and download that one. Okay, so all 3 of those things should be on your computer now.
Look what it says.
You don't want to open those directly. You want to open those in Google Earth. So open Google Earth first.
Okay.
From the app that you downloaded though, okay, not from there. Why don't you go to your downloads folder? Do you know where to find that at the bottom of your screen?
I'm not.
It's usually like there's 3 blue folders that says like documents and one is downloads. Or you can go up to your magnifying glass and type in downloads there. The magnifying glass is the upper right hand side of your computer window.
Oh, okay.
And type in downloads and then open the folder that's the download folder. Are you stuck?
It doesn't show anything.
Let me show you. Okay, let me show you on my can you stop sharing and then I'll show you my screen. There should be a red button on Zoom that says like stop sharing. Good, okay. I'm gonna share my whole desktop here. So can you see my buttons down at the bottom here?
Yeah, no. Wait.
Can you see my whole screen?
No, I just see, wait. I don't know what's going on here.
You need to be in Zoom.
Yeah, I'm in Zoom, but it's showing you in a small.
Okay.
Small corner. It's a little weird.
Okay, so find. I can't. Help whoever else is out there. Help me out. Can you guys see my whole screen?
Yeah, it just. I don't know why.
Yeah, we can see your Zoom screen.
But can you see like my
yeah, we
doc?
can see your desktop. Yeah.
And okay, so the doc. Where I'm trying to send you, Ashanti, is down here at the bottom. In your doc, you should have a downloads folder. If you just click on that and then open it, you should have those 3 files there. I don't have anything because I haven't downloaded anything.
Wait, go back.
So go down to the bottom to your doc, and there should be a blue folder that says downloads. If you got stuff in it though, it might not look blue. It might look a different color. So, but it'll say downloads if you hover your mouse pointer over it. It's right about here.
Yeah, mine doesn't have that, but let me check in my settings.
Okay, or go to your spotlight up at the top, your spotlight search that I'm showing you now, and then type in downloads.
I'm not able to see. Let me see. Oh, I see now.
Can you see my screen?
Yes.
Okay, good. So I just typed in downloads, and you should probably just have one. I have, mine's a mess. Let's see, is it this one? So hopefully you just have one download folder. Click on that one and open it.
I don't know why my computer is something.
Okay, we might need to sit together and do this at maybe like go back and forth sharing our screens. Can you stay with me a few minutes after class?
Yes.
Okay, let's do that then. You've got part of the way. You've downloaded the 3 files that you need. We just need you to find where those files go. Okay, as soon as you can, then what you're gonna do, or I mean, you have to install Google Earth first. So it's like a .dmg file that you gotta double click on first, and that'll install Google Earth. So I might have you share your entire desktop with me later, okay?
Okay.
So for now, let's just pause. Does anybody else need help with that, or hopefully that answered some people's questions?
Can I give some advice?
You bet.
So if you're having trouble opening up the CAMZ files or the CAML files, I
Yeah.
noticed on my computer, the default application that some of them want to open them with is Photoshop for some reason. But I noticed that if I have a MacBook, if you right click,
Yeah,
a menu will come up and it will say open with, and
exactly.
then you select open with Google Earth Pro. That's what I do for all of them.
So I'll just do an example of that since you can see my screen. Okay, so I'm gonna grab the California geology file and download that. It's gonna go to my desktop though, because that's how I have my computer set up. And then finding it is another issue. It's here. It's here, it's here. I'm gonna hide these. I'm gonna hide that. There it is, way back there. Okay, so California. So the right clicking, this is what comes up, you guys. So if you don't have a mouse that right clicks, hold the control button down and it does the same thing. So do control click to get this window. And what you get is open with is what Kay just described. And then you can, if it doesn't show Google Earth Pro here, you can go to other and then navigate to Google Earth. But the easier way to do it is if you've got Google Earth running, let me go back there. I've got Google Earth here. Just go to once you've got Google Earth open and you're looking at it, then go to the file menu, go to open, and then navigate to your file. So I can do that by I just go to my desktop and I sort by the date so that the latest thing I downloaded is at the top. That's how I kind of cheat it. And anyway, there it is, California Geology. And then you just click open and that's all you need to do. So I think that's a little bit simpler than trying to navigate through the right click process to choose the app, but whatever gets it done, right? Whatever you guys can manage to find. Any other questions about that for now? So it's really important that I think it's important that you follow the instructions that I gave on that lab page, on that lab folder page on iLearn. I'll go back there right now. So use one of these links to grab Google Earth to download it. You're still going to have to install it by just double clicking on the icon that you end up downloading and follow the instructions there. That should open it. And then you need to download number 2 and number 3. Those two.
I found my downloads, but nothing's in there.
You found your download folder?
Yes.
Okay, so does that have the Google Earth app in it?
No, it does not.
Okay, so try downloading that again. And hopefully that goes to your download folder. What happens if I right click? No, that's not gonna work. Yeah, I think it's best if you just click on that. I can try to see what it looks like when I download it. So I'm downloading it again.
You said 2 and 3 also, right?
Also 2 and 3. Mm-hmm. Okay. So number one, get Google Earth open and running.
Maybe it's saying that because it's saying no preview available.
You just download it anyway. You don't need to preview it because you know it. The only reason your computer's saying that is so that you're aware in case like you don't know what it is you're downloading and you're trying to worry about the safety of your computer. But like this is I'm sending you to, it's a good link, it's safe to download. So go ahead and download it anyway. Okay, then get Google Earth running. So you're gonna have to double click on, it's usually called it's a .dmg file that the apps start off as. You gotta like uncompress them and open the app. Sometimes apps ask you to drag an icon to your applications folder. So if it has that instruction, you need to do that. Sometimes it just starts. And then when you've got Google Earth open, that's when you're gonna navigate. I think the easiest way is to go to the file menu, go to open, and then navigate to your download folder, and then one at a time, click on the California geology file, and then click on the Earth topo file. Okay. Are other people having trouble with this same thing or a different issue maybe? I will take silence as nobody's having trouble. You can also raise your hand in the participants window or, you know, give me a yes or something in participants and I can come to you. But what happens is when you open these files in Google Earth, you see how there's a box next to each one. So I've got these turned off. You can turn them on and off by clicking in that box. So when it's not clicked, they're not showing. When they are clicked, they are showing. Come on. So this is what the California geology map looks like when you zoom out. You don't want to look at that to answer every single question. So you're going to want to turn that off sometimes, especially when you start to look at the topography. So I'll click on the topography one. And you can't really see, you can't see the contours until you zoom in pretty far. But if you zoom into a place, and it's a little bit slow just because I think I'm zooming and I'm asking Google Earth to do things. Okay, here it goes. All right, be patient. Now you should be able to see topography anywhere you want to go in the US, not just California. And then one of the questions in Lab 5A asks you to navigate over here. I'll change this. So it asks you to navigate. There's a search button right here on the left. I assume you can still see my Google Earth window. There's a search button here, and then there's this gradient button. This is transparency. So if I click on that and then move this slider, you can go from completely opaque, where you're just looking at topography, to partially opaque, where you can kind of see the satellite image of Google Earth through the topographic map. Sometimes that helps you to, like, in this case, like for example, the hills that are right here left of, you know, in between these two neighborhoods, these are some hills. And when I've got the topography map open, you'll see that there's a bunch of really closely spaced contour lines that tell you that those are hills. And they're spread out much more where those cities are, right? You can kind of, you see through that a little bit. So some of the, like this part of the neighborhood is actually built up into the hills. You can tell that by just looking at the Oh, I see. There's like a little flat part behind a, so they must come up this way and then fill in these flat spots with the houses. So that's to answer one of the questions, but I don't know where I am right now. Let's go to some of the first questions ask you to go to Mount Hood, Oregon. So it's going to fly you there. Whoop, okay. So let's see. All right. So it loaded the topography after I landed in that spot. So now I can see the topography, and I've got it, the vertical exaggeration set so that you can see that there's an actual mountain there, that Mount Hood is a pointy peaked looking volcano. If it doesn't look like that, go to your preferences window. So Google Earth Pro file, or sorry, Google Earth Pro menu, then go to preferences. And then here, it says elevation exaggeration, also scales 3D buildings and trees. I have mine set to 1, and it should be a number between 0.01 and 3. 3 is really crazy exaggeration, and it will make things look unnatural. So I think 1 is a pretty good number for doing this lab. So just put 1 in there, and then you can apply it or just hit OK. And then that should give you the topography popping up like this. Now, another thing that you can do to kind of see the topography is to tilt your image. Oh, I'm doing it the wrong way. So the very top, like where the north compass is, these 2 arrows, the up arrow tilts the image. And then you can like zoom in, you can tilt it more. I'm gonna zoom in a little bit more. I'll tilt it. So now you can really see there's a volcano there, right? Okay. But I don't actually like to work with it tilted. I usually like to work with mine being completely flat. Oh, check it out. You can see the other volcanoes of the Cascade Range up here. Sam? That's really cool. You can see part of the chain of volcanoes right there. Anyways, you have questions to answer about Mount Hood. So I would go back, press and hold the down arrow until it stops. And that will mean that you're looking straight down on your Google Earth image. Okay. I hope I'm not confusing anybody by showing you these settings. You know, remember that this is being recorded. So if I'm going too fast, or if you want to refer to this later, you can go to the recording and get your answers there, and, you know, pause and look some more. While we're in this view, I thought I would just point out a couple things that stand out to me geologically. You've got maybe I'll turn off the topography for this. Okay, so Mount Hood is here. It's mostly snow covered, but there are a bunch of features that you can see. Like, check this out. Do you see this like string of, I don't know what to call it. It's a big volcanic, it's either a lahar, we haven't learned these words yet. It's either a lahar, which is a volcanic mud flow, or this is a result of a pyroclastic flow, which is like a hot ball of gas and rocks and ash and other material that's like an avalanche down the side of a volcano. It's the stuff that follows the ground. It's not the column, the eruption column that goes up into the air with the ash. So there's like an avalanche of materials sometimes. sometimes it's a mud flow, the lahar, which is basically, you see it's covered in snow. So if you get a volcanic eruption of hot material that lands on snow, you're going to melt it. And that's going to give you basically a river of mud and trees and other debris. They're really dangerous, actually. But see how this flow actually follows this little ravine. So, or these two ravines. There's a little creek there, another little creek, and they come together at the bottom, and then they kind of like spread out. It must be pretty steep topography here, and then it spreads out where the landscape gets flat again. It covers a road, and it actually covers a road that separates these two towns. I don't know what they are. There's another town there, but look, they're all over. There's another one here that goes really far from the volcano. Like, how far is this? Let's measure with the ruler. Okay, so that is, let's do it in miles, since you guys are used to miles. 6 miles. So it spreads out 6 miles from the volcano. This one up here, let me get rid of this. This one looks like a similar distance. There's a big city here, Parkdale, and there are some of these flows that have gone down this far, almost to the town. I would say that town has a very definite volcanic hazard to be aware of. Specifically, those lahars, the volcanic mud flows, and the pyroclastic flows could reach Parkdale and cause a lot of chaos and damage. But those are just some things that I see looking at the satellite image. I mean, they're all over. Like, here's another smaller one, other smaller ones here. They all follow the ravines, the valleys, or the stream beds, because gravity, just like anything like water in a river, is going to go to the lowest gravitational point. It's going to go to the lowest point it can reach, which would be the bottom of a stream bed. And then it'll follow that out away from the volcano. And then they can spread a really long distance away from the volcano. We'll get back to like looking at hazards like that later when we talk about igneous rocks, for sure. We'll talk about hazards associated with volcanoes. There was a question, I went over this at some point. You can see my transect line that I did there, actually. If I click on it, I can show the elevation profile. So even though I haven't done it recently, it's like saved in my Google Earth. I can show the elevation profile for that line. And do you see how it shows trying to point with my finger, ridiculousness. Okay, it'll show a red arrow along this line as I move along a profile. So it shows you exactly where you are on the profile on the actual map. Okay, so this tells you that the distance that this profile covers, and that includes going up the mountain and down the mountain, is 13.7 miles. But that includes the elevation gain and everything. If I measure it with the ruler tool, the same distance, like this, look at the distance, 12.51 miles. So it's shorter, which it should be, because you don't have to go up the volcano and down again. So when you do this yourself, make sure that that you're comparing the distance in your topographic profile, the elevation profile, and you're measuring with the ruler tool to get like the distance as the crow flies, as I say. Is that clear to everybody? So I've shown you a couple of things, a couple of the questions from your lab. So the elevation profile and this gradient to fade out the topography layer or the geologic map layer. I can show, maybe it'll show up a little bit better if I show you the geologic map. Oh, wait, we're in Oregon. We got to go back down to California.
Wait, I had a quick question before.
Sure. You want me to stay in the hood?
Yeah. So one of the questions was us comparing two of the transect lines, like of different sides of the mountains. I think I figured it out, but I was hoping if you could maybe demonstrate like creating one for one side, because I know I created the whole line going through the entire mountain. I was just confused on how to compare the different sides.
I'm not sure I know which question you're talking about.
Oh,
What question is that?
let me look at it really quick, just 1 second.
Okay. I'm gonna go grab the lab while you do that. Lab 5A. Oops. Okay, so here's the lab. So it asks you the elevation of Mount Hood. You need the topo map displayed to answer that. Actually, Google can tell you too. So there's two ways you can answer that, because you should, okay, check this out. Okay, so I'm gonna zoom in closer to the mountain. So if I wanna know the elevation of Mount Hood, I can put my pointer at the top of the mountain and look, and then I'm gonna take, wait, is that right? Yeah, I'm gonna take my pointer away to show you. Down here, it displays the latitude and longitude of the location of my pointer, and it gives you the elevation of the pointer. So I'll take my pointer back up here and go to the top. Okay, when it says 3,000, I've clearly gone beyond the top. Okay, there, 11,156, something like that. Or what you do is show the topography, and then I need to make this flat again to read the map. Okay, and then let's zoom in. The topography map should, I thought it did. Maybe I need my glasses. It had the elevation written on the map, didn't it?
Can't you click the thing on
Oh,
the,
click this, you mean? Yeah,
yeah,
we could try that too.
and then I think you click like the green one.
I'm trying to. Come on. There we go. Very good. Elevation, 11,239 feet. That's a third way to do it. So you can either read it, if the elevation of a peak is listed on the topo map, you can read the topo map. You can click on these informational things that come up, and that gives you it. Or you can get close by looking at the elevation on that's displayed at the bottom of your Google Earth screen. But that's just an approximation, because you don't know exactly where the highest peak is when you put your pointer there. Okay. Does that, did you find the question?
Yeah, the question is 13 and 14. So it's which side has a greater average slope when comparing the west side and I think the east side.
I don't think you need, do you need to do a separate profile, or can you just use this one?
I wasn't sure. That's why I was slightly confused.
Yeah, let's see. Okay, so yeah, this gives you, it shows you a maximum slope and it gives you an average slope. You're right. So probably the smart thing to do is to draw two separate lines. So what this is saying is, though, you can draw those two It says the east and the west. Is that right?
Yeah, the east and the west. And then for the approximate length of the entire profile, would we use the ruler tool like you showed us but before?
Yeah, so I think it
Okay.
asks you both. The
Yeah.
straight line distance is the one using the ruler tool.
Oh, okay.
What is the approximate straight line distance between the 2 points? You can change the, yeah, right. So simply this, you can click the same distance as your other profile and see the distance there. Ideally it's in kilometers, but like I understand you guys are used to miles, and so if you want to answer in miles, that's okay. But that's the straight line distance. But remember, the profile distance is different. It's longer because you've got to climb up the mountain and back down. Okay, so to answer the slope question, I suppose the easiest way would be to draw a new transect. Which one is it? Image overlay, add a path. Okay, so I can draw a parallel path like that. And then we don't need this. Ah, I should have saved it. Okay. Okay, I'm gonna save it. And now I can click on that line to show the elevation profile. And that's gonna give me the average slope of that side. You see it's displayed right there? It gives me a maximum slope and an average slope. So that would be the slope for the west side. And then what I would do to get the eastern profile is simply draw another, I shouldn't say simply because it's not necessarily simple for you guys. Okay, click OK. And then all I'm doing is I'm control clicking, or you can right click on this line, show the elevation profile. Then average slope, 23.1%. I think that's a more gradual slope, isn't it? Than the other one that I just read?
Yes.
And then, yeah, and then the maximum slope is 65.7. Don't worry about the negative number. That's simply because it's going from higher to lower on the profile. If it went from lower to higher, it would be a positive number. So 65.7 is your maximum, 23.1 is your average. I don't know what this negative 26 is. Okay. Does that answer your question?
Yes, it does. Thank you. And then for the approximate length of the entire profile?
So you can either, right. So you can either
Do the ruler?
well, so I think it's asking the ruler question. So you want to just follow, do the same
Okay.
line, draw a line parallel to the line that you drew for the profile and make it the same length. And then you can compare 12.6 miles approximately for the line that I drew.
Okay.
Your line might be a little different.
Thank you.
You're welcome. Any other questions about Lab 5A?
I just had one quick one real quick.
Yeah, you bet.
For the latitude and longitude,
Uh-huh.
it will tell us at the bottom you said the
It does. For wherever your pointer is. So yeah, so as I move around, you see how the numbers change? So if you wanted the lat long of the top of the peak of Mount Hood, I could just hover my pointer there, and then it gives me 45 degrees, 22 minutes, 38.12 seconds north, and 121 degrees, 41 minutes, 51.90 seconds west.
Okay.
Which question does that answer on the lab?
Oh, it was number 2.
Oh, it's just number 2. Okay.
Mm-hmm.
Let's scroll back up there and then get rid of this. So, oh, it was the peak. Okay, maybe I remembered that somehow. Yeah, so go ahead and try that yourself and jot down the answer. Mostly this first part of the lab is just getting you used to using Google Earth. And then you're going to apply it in 5B. So I asked you guys on Tuesday to please start 5A if you hadn't already. If anybody's stuck on another question 5A, please ask right now, and I'll answer, and I'll give you a quick answer now so that you can make progress after class. I'm also going to be around tomorrow. I have to have a shorter study group tomorrow. It's only from 11 to 12 because I have another meeting I've got to go to. That's and it's important for undergraduate advising. So just 1 hour, but from 11 to 12, I'm happy to answer any of these questions, or probably better to answer questions for 5B, because I hope that you have started 5B by then. There was some confusion about like the name of the glacier and what the blue and brown lines meant, the brown contours. So the glacier name is actually printed on the topo map. So you need to have your topography layer turned on, and then you should read the glacier on the southwest side. So you've got a compass at the top. It only shows you north. East is to the right, west is to the left, and south is to the bottom, okay? So the southwest corner is going to be the bottom left corner, this one, labeled right there, zigzag, okay? Now, there was a question about blue contour lines over the glacier. I don't see blue lines right now, and brown lines elsewhere. So just take this part of Mount Hood as an example, in between the glaciers. Where there's no glacier, you're looking at rock or soil because it's bare ground. It's not covered by ice. So that's all it's asking. It wasn't a difficult question, really. It was almost too simple. So it's just saying, what do the brown lines represent? In this case, they are the elevation of the rocks, the soil that are on the sides of the volcano. All right. So let me, okay, I'm gonna move away from Mount Hood now, unless anyone else has a question. You can stop me still. I'm gonna zoom down to California. So let me go to San Francisco. And it's gonna fly there. And I already have the the geologic map showing. So the cool thing about the geologic map is, I wish it was a little more colorful. They didn't distinguish between the different parts of California very well because there's like too much brown. But if you click on any color on this map, it's gonna pop up with a description of the rock unit that is represented by that color. And it gives you a bit of information about that. So in this case, it's saying this is the Franciscan complex. It's part of the Coast Ranges, and it includes Cretaceous and Jurassic sandstones with smaller amounts of shale, chert, limestone, and conglomerate. It includes Franciscan melange. Melange is from the French word for mixture. I've been describing the Franciscan melange to you. When we talked about, when we looked at the Point Bonita pillow basalts, that was part of the ophiolite that's in Marin. But that in other areas like Ring Mountain and Tiburon, where I've talked about there being mantle rocks, so pyroxenites, mostly it's pyroxenites, serpentinites. Those are metamorphosed mantle or slightly just altered by hot fluids in the oceanic crust. That's a mixture with lots of different rocks in just a single area. I'm talking about right in here. So Point Bonita is out here somewhere. I don't have it at the top of my, oh wait, it's right here. It's at the tip of the lighthouse, isn't it? This is Point Bonita. Point Bonita Lighthouse. I'm trying to hover there. So those pillow basalts are out here. And then those radiolarian cherts, the red bedded cherts, are in this area facing San Francisco, but on the Marin side. And then if you go up here to, is it all the way out there? It's not all the way out there. It is up here. Ring Mountain is right in here. This is the melange in the bright pink. So it is a bunch of, it's a mixture. You see grassy hillsides with outcrops of more resistant rocks that stick up out of the grass. You see some bare outcrops, but it's a big mixture of rocks from the ocean floor, from the mantle, from the continental crust even, all in a very small space. It's probably because it's one of these slices that come up buoyantly from the mantle, like as it's subducting, some of it makes its way back, and it's faulted and fragmented as it does that, and it's kind of messy, and so you end up with a mixture or this melange. The lavender colored one are the ultramafic rocks. So that's the mantle rock that it's showing you. In this case, it's probably mostly serpentinite. We're going to look at all those rock types when we get into rocks and minerals. For now, you can think of it as either being related, the rocks as either being related to the mantle, to the oceanic crust, or to the continental crust, I suppose. Okay, so that kind of gives you like an idea how you use this geologic map. So you can find the name of the unit, the kinds of rocks, and the age of the rocks in any place. That will help you with the last part.
Can I make a comment?
You bet.
I really like this overlay. I actually ended up using it in my Techniques in Earth Science class for a little presentation I did on Mount Lassen. Nice. So I found that this is like really useful, not just for the content in this class, but being able to apply it in other classes.
So true. It really is. Yeah, you could, there's so much data that is out there that you can layer into Google Earth, that even if you're like if you're an engineering major, let's say, I'm sure that there's like city planning data that you can incorporate. And you know, in your case, you went to Mount Lassen and you looked at the geologic units there.
Yes.
To talk about that. Cool. Okay. Yeah. Any other questions before we get going? Ooh, we've used a lot of time. That's okay. It's okay. Today, if we're done with questions about Lab 5A, I'm going to put this away. I'm going to stop sharing my entire window and switch over to the lecture slides, if that's okay. All right, so nope, not plate. What am I doing? We're in the next one. We're in earthquakes and crustal deformation. Excuse me, there's somebody at my door who I told him I can't meet today, and he's here anyway. And I told him I'm teaching a class. I can't talk to you. Okay, that deals with him. I told him, Jesus, people don't listen. Okay, this is now, here's where we're gonna start. Okay. this is a seismogram that this guy is holding up, and this is a one of the instruments that actually records some of the data. So a seismometer. Geophysicists are the ones who study earthquake waves and how they travel through Earth, and they look at the hazards associated with earthquakes too. This is a seismograph that shows you.
Professor,
Yeah.
are you sharing?
Oh, it's not sharing. Okay, you got me again. Yes. Yes, yes, yes. Thank you. Too much going on. Okay. Here we go. Let me switch that in. Okay, so here's this dude. All right, so he's holding a seismograph, and it's showing you kind of like background noise there and the arrival of an earthquake. So this is the first wave, or the P wave. It's also short for primary wave. We're going to look at these in greater detail. So this is the first smaller wave to arrive. That's the one that travels fastest through Earth, therefore it arrives first. Then you get the S wave arriving. That's the big one. So the size of the amplitude of those waves, of the line here, the height of this wave, it correlates to the magnitude of the earthquake. So there's the P and the S wave, S for secondary wave. It's also a shear wave, so that helps. It's side to side motion instead of, oh, I didn't get a slinky ready for you guys. I'll try to locate a slinky for Tuesday, because slinkies are like a good way to demonstrate how seismic waves travel in the earth. And then after that, you get the even slower waves, the waves that travel along Earth's surface. So the first two are called body waves. They travel through the rock in the earth in all directions. But some waves reach the surface and then they just bounce around along the surface. And those can cause a lot of damage too. We'll look at those together as well. But overall, this summarizes everything in your textbook. What I'm going to cover in this lecture, which is going to take place over 3 days. So we're going to talk about this on Tuesday and Thursday next week. We're going to talk about different types of faults, the earthquake seismology, so how those different seismic waves work. We're going to talk about locating earthquake epicenters, how you evaluate the magnitude of an earthquake. We'll talk about two important earthquakes out here, the 1906 earthquake in San Francisco. It actually, the epicenter was just outside the Golden Gate in the ocean here, not far. And the 1989 Loma Prieta earthquake, that was a bit smaller, but still significant. We're going to talk about what controls ground shaking. So literally what you feel in an earthquake. Other hazards that come along with earthquakes, like landslides, fires. Fires is actually what caused the most damage in the 1906 earthquake. It wasn't the shaking itself, it was the fires afterwards. Why? Because it broke the water lines and they couldn't put the fires out fast enough. They tried pumping water from the bay even too, but we'll get to that. All right. And something called liquefaction, where soils that, like the bay muds that are all around the edge of the bay, those have really intense shaking because they're loose sediment that are filled with water in the pore spaces. I said that. Earthquake prediction and the probability of having earthquakes on different segments of the fault. Crustal deformation, including faulting and folding. I just realized I want to add in locked and creeping segments of faults. So some faults creep along really slowly, like the Hayward fault that we've got in the East Bay is normally there's a big long creeping section that passes through Hayward and Fremont. So it goes slowly, doesn't generally have large earthquakes. The stress is released gradually over time versus lock segments that the stress builds up across the fault and all of a sudden it breaks in one earthquake and it moves a large distance in just a few seconds. We're going to talk about all of that. So there's a lot to think about here. Okay. Earthquakes. I have a little video. This shows you, I think these are magnitude 5 and up. 7 and up, 7, 8, 9. So it's got a scale right here that shows the smallest circles being magnitude 7, medium circles magnitude 8, and the very large circles are magnitude 9. And the video is going to go from, does it go from 1960 through present, I think? 20th century. So it must start at the, well, let's see exactly where. 1901. Okay, it does start there. So this is going to show you it's 1 year for every second is what it's showing you. These are all the earthquakes, the very large earthquakes that happen around the world in the 1900s. That sounds like it was forever ago, saying 1900s. It was just there. Don't know what that was. There are a lot of them. What kind of plate boundaries are these really large earthquakes happening on? I'm asking you guys, where are you seeing most of the these large earthquakes? What kind of plate boundary are they falling on?
Isn't it like the Pacific plate boundary?
Okay, so around the Pacific plate, totally. That's the Ring of Fire, yeah. The Ring of Fire is telling you about the chain of volcanoes that goes around the plate. But okay, now it's going crazy. Is that real?
There's a lot that are happening at divergent boundaries and also at subduction zones.
Those must be smaller. Okay, so I think that when we got to was that in the 60s? It really changed how it looked. When we got to the 50s, this must be when we started putting more instrumentation in. I think it's starting to show us really small earthquakes too, because that's so many. And yeah, you're right. On the divergent plate boundaries, there are even smaller circles showing up on this. So this is going down to magnitude 5, I think, or it may be even smaller. But the numbers seem to have increased, I think. It became more rapid fire. Look at how crazy it is. Because we started measuring them better. We had instruments around the world. That's just a crazy number of earthquakes. If this doesn't prove to you that the plates are moving on Earth, I don't know what would. Wow, that's impressive. It's still going. I'm just going to talk about it. So there you go. 99 years of earthquake epicenters. That was wild. What I was hoping that someone might say is that most of I'm going to scoot forward to like the 40s here. This is happening on subduction zones, right? The Ring of Fire is there. The Pacific plate is really active tectonically because of the subduction zones that surround it. So in these cases, this is the Pacific plate subducting beneath other smaller plates here. But there are other smaller plates, like there's a plate behind the Japan arc that is subducting beneath China. And then we have the Nazca Plate subducting beneath the South American plate. So there, yeah, everywhere you see a subduction zone, wherever you find a subduction zone, you're getting the very large quakes. Then it added in the smaller ones, and we started seeing, then the divergent plate boundaries, those mid-ocean ridges started to show up better. Okay, I'm gonna move forward. So in California, we've got, there are faults everywhere. They're littered all over the place. But we have some more major faults. And those include the San Andreas that you know about, the Calaveras and the Hayward faults that are in the East Bay. This is the Garlock fault that is almost perpendicular to the San Andreas. That goes out into the Mojave Desert and sort of, it offsets that southern part of the Sierra Nevada, pushes it out to the west. And then we've got the Eastern California shear zone here that separates the Sierra Nevada mountains from the Basin and Range province, which is that province of continental rifting. So there's rifting out here that's, you can see it, like it's spreading, like pulling apart and forming these linear basins and mountains, ranges, right? This Eastern California shear zone is probably where the deformation is going to change. Over geologic time, I think that this is going to become a more major player in California tectonics. We might see the plate boundary shift from the San Andreas to the east of the Sierra Nevada, and maybe even, you know, to separate California from the Basin and Range. And that would start from the Salton Sea, like coming out of the Gulf of California. So the new plate boundary might be here. But that's a long way in the future, and that's speculating on what might happen. We've got, I want to focus mostly on the San Andreas, but I'm going to talk about the Hayward Fault too, and the Calaveras. Those are important. I showed you an image last Thursday of the San Andreas that looked like this really sharp line in the earth. This is part of that from the Carrizo Plain. And a cool feature that you can see here, this is Wallace Creek. And the creek is coming down here out of the mountains. And when it hits the fault, look what happens. The fault, or the creek runs parallel to the fault, and then it finishes flowing toward the ocean here. So it's offset by a pretty large distance. I mean, it's several football fields, 2 football fields, maybe not several football fields. I think you're going to measure this in your earthquakes lab. I'm going to see how that lab develops, but you can tell the sense of shear. Okay, so this is a transform fault that separates the North American and Pacific plate, right? But it's also a kind of strike slip fault. That's one name that we give to a type of fault, like transform faults that have horizontal motion. So you can tell the sense of motion, whether it's a right lateral strike slip fault or a left lateral strike slip fault, by how it shifts the earth. So imagine you're standing here in this field and you're looking toward the mountains. This is a mental experiment. Or let's say you're standing in this creek. Better if you're standing in the creek. Stand in the creek, look toward the mountains. Where is the rest of the creek bed compared to where you're standing? If you're here and you look across the fault, the rest of the creek is to your right. Everybody see that? And you're not done with the mental experiment. Now I want you to stand on this side of the creek and look across to this field, or look across to this side. So stand in this creek bed and face the screen, or face this creek. Which way has this creek shifted?
Right.
Also to the right. Yeah. So it doesn't matter which side you stand on or what your perspective is. You're always going to get the same answer. This is a right lateral strike slip fault. And that's what accounts for, okay, if you look at the geologic map real quick, here's the fault going like this. Okay, so here's San Francisco on the North American side of the plate, of the fault, and LA on the Pacific side of the fault. Because this is a right lateral strike slip fault, this side, the Sierra side or the San Francisco side, is going to move to the right or south. And the LA side is going to move to the top of the screen or to the north. And that gives you this right lateral strike slip motion. So LA and San Francisco are gradually getting closer by, let's say, I think it's around 5 centimeters every year. So that's another piece of trivia I bet you didn't know, or you can have fun with your friends. So that's how you determine the slip sense. That's what that means. And it applies to other smaller faults. It doesn't have to be a transform fault that's a plate boundary. Okay, I wanted to show you a few other things about just using the geologic map of California, and also comparing it to this. This is like different geomorphic terrains in California. So different landforms, let's say. So you have the Central Valley. Okay, that's a valley. That's the landform. And you have the Sierra Nevada mountains. That's one landform. You got the Basin and Range out here with Death Valley. That's a landform. You've got the Mojave Desert south of the Sierra Nevada. This is a different landform. You have the Northern Coast Range and the Southern Coast Range. These are the ones I wanted to focus on right now. The Southern Coast Range is if you look at the geologic map, that purple unit is mostly orange on the geologic map. And this North Coast Range is mostly green on the geologic map. And what separates them is the San Andreas Fault. What I want to point to is this orange unit has been shifted north along the San Andreas Fault from Southern California. So over geologic time, over the 30 million years, 25 to 30 million years that the San Andreas has existed, it shifted this distance, like basically from LA to north of San Francisco. It's hundreds of kilometers. This part, the orange bit, is given a name called the Selenian terrain, like Salinas. It's perfectly good. Salinas is down here south of Monterey, right in here. And those rocks are all related to the southern Sierra Nevada and south. And these green rocks here are actually, those are the ophiolitic material that was scraped on land or abducted onto the land while the Sierra Nevada range was forming. So these are older, these are related, but older parts of the geology, let's say, yeah, pre the San Andreas Fault. What do I want to say? So this is related to subduction, basically. And these are only here because of the motion along the San Andreas. See these red rocks here south of Monterey? And there are a few red bits in Point Reyes, Montera Mountain right here, south of Pacifica, Santa Cruz, Monterey, Carmel. Those are all Sierran granites that came from down here. So you can literally walk out and touch rocks that have moved hundreds of kilometers north along the San Andreas. This is important because I'm going to ask you questions in your lab, your next lab, the shorter one, that are going to ask you to measure offsets along the San Andreas. So I'm going to give you some piercing points, like one point on one side of the fault matches up to another side, because you can measure the age, get a uranium lead age of that granite. You can also measure its chemistry to see how much silica it has, how much iron and magnesium, the aluminum, sodium, potassium, all of those elements to see, is it chemically the same as one of these granites down here? And there are certain places that have been matched up very nicely across the fault. The Pinnacles, if you've ever been to Pinnacles National Monument, I think it's a national monument, not a park. That is a piercing point on the San Andreas, or used as a piercing point. We'll talk about that later. Okay, so this says what I just said, but it shows it a little bit differently. So in this case, the Selenian block, these are the southern Sierra Nevada rocks, are in dark gray. And then the Franciscan rocks that are related to the Sierra Nevada, these are the metamorphic rocks related to the Sierra Nevada formation, those are in light gray. And then, so this is a little bit easier to see how different the rocks are on either side of the San Andreas. This map also happens to show a couple of other features that I'll just mention real quick. It shows creeping segments of faults. So here, between San Juan Bautista, let's say that might be 100 kilometers south of San Juan Bautista, this section of the San Andreas and this part of the Calaveras Fault and this part of the Hayward Fault, so the part that goes through the East Bay, are all creeping segments of the fault, meaning they shift very slowly during small magnitude earthquakes. Some of them you don't even feel. Occasionally you get like a magnitude 2 or 3 that might shake you awake in the night. There is potential for much larger quakes, but in general, they're small and it's creeping along. And I'm going to show you evidence for that creep in the slides at some point. Here's, okay, so this is just like the last map, but the Selenian block is in pink. And there's Point Reyes there. Here's Montera Mountain. Here's Monterey Bay. And this is what it would look like if you were to reconstruct, like put those rocks back into place. So we're gonna move those rocks south we're gonna move the Pacific plate to the south again and restore those rocks back to where they were. You'll see that they then line up with the southern Sierra Nevada. These are the Point Reyes rocks, lining up with all those. So there are different slices, let's say, of earth that have moved different amounts. But this is where they came from. So they've moved that distance. These rocks have come from here and now they're here. They're granites. These rocks have come from here and now they're along here. It's an impressive amount of change over geologic time. All right, I have some, we're gonna look at, I'm kind of, in these next slides, I'm gonna introduce kind of the topics that we'll talk about next week also. So I'm going to touch on a bunch of different things that we will come back to. This is the image I showed you before, the San Andreas Fault. This is, it's a world famous example. People in Europe, when they're teaching transform faults and plate boundary types, they're showing pictures of the San Andreas Fault too. So we're just kind of lucky in a strange way to live here where we can actually see all of this. That section comes from Central California. And I just want to point out the other plate boundaries, the other features that we've got going on. So there's spreading happening in the Gulf of California that's separating the Baja Peninsula from mainland Mexico. Then the San Andreas comes out of the Gulf of California through the Salton Sea, and then to Cape Mendocino, that's right here. It goes offshore where it reaches a triple point between the subducting Juan de Fuca plate and the Pacific plate here. So there are three plates that come together, the North American, Juan de Fuca, and Pacific plates. That's why it's called a triple boundary. And you also see, okay, so these are spreading ridges here separating the Juan de Fuca plate from the Pacific plate, and those transforms that separate the offset segments of the mid-ocean ridge. Here's the subduction zone that is forming those volcanoes like Mount Hood. And then these fracture zones are just the scars left from being a transform from these offset segments. So earthquakes can happen on these fracture zones too because they're weak places in the crust. Okay. We're going to look at details of the seismicity related to the 1906 and the 1989 earthquakes. But just in general, this is a map showing about the last 30 days of earthquakes in Central California, Northern California. There are a lot of them, and it looks like this all the time. If you were to go to quake.usgs.gov, that will take you to the U.S. Geological Survey's page. Here, I can type it here. Quake.usgs.gov. Of course, it's black. Okay, there. So if you were to go to that website, that'll show you today's earthquakes. Yeah, and it breaks it down into, in the last 24 hours, I think are red. There's the last week, which might be yellow, and then it gives you like white epicenters for even older quakes. Anytime you feel a quake, you can go to this site and report what it was that you felt, and then find out information about any of these earthquakes by clicking on these epicenter spots. And I'll show you I'll show you how to interpret that information. Okay, so there are some primary hazards that we're going to talk about. We're going to talk about the ground shaking. That's one of the most important hazards, right, that comes from earthquakes. And then ground rupture. So the surface of the earth can rupture. It might open up a hole big enough for a cow to fall in, let's say. You might fall in, but you're not going to the Earth's core or anything. You're not falling through the center of the earth. It's literally just going to be a crack in the surface of the earth that it looks like. Those ground ruptures can be 12 inches long, or they can be 25 feet long. During the 1906 quake, there was one segment that was 25-foot long ground rupture in Northern California. Really impressive. Secondary hazards include things like landslides, because landslides can happen when you shake the earth. And if there's been some recent rain that's filled up the pore space in soils, that can help create landslides. Fires can be triggered by breaking gas lines, and then you break water lines too, so you can't put them out, like in the 1906 earthquake. Liquefaction is when soils are water saturated, like bay muds that surround the edge of the bay, that experience more intense shaking than other places on the surface. Tsunami can also form. Usually not with a strike slip fault though, because the motion is horizontal. You need vertical motion somewhere that's going to offset the ocean floor, to generate a wave in the ocean like that. We'll talk about that too. We should discuss the probability of earthquakes happening on different faults and on different parts of the faults. I mentioned at one point that like the Loma Prieta epicenter was in the Santa Cruz Mountains, right about where my pointer is here. So that actually released a lot of the stress on the San Andreas as it passes through the Santa Cruz Mountains. And that reduces the probability of another large quake happening there anytime soon. The US Geological Survey, every once in a while, publishes a map like this that shows statistics for large quakes. And this says there's a 63% probability of having an earthquake of magnitude 6.7 or higher in the Bay Area between now and between 2007 and 2036. That's only 16 years away. We've got the Hayward Fault that extends to in the North Bay. It's called the Rogers Creek Fault there. There's a 31% chance of having an earthquake on that fault, a large magnitude earthquake. This is going to cause a lot of damage. There's a 21% chance on this segment, the segment of the San Andreas that goes through the Santa Cruz Mountains, up the peninsula, and up through the North Bay. So it's less than the Hayward Fault. So in the Bay Area, the biggest chance of the next big earthquake, the highest probability is going to be on the Hayward Fault, not the San Andreas. It's kind of counterintuitive because I think we think of the San Andreas as being the big fault around here. The color coding on this also indicates the magnitude or the increased probability. So the more red, the higher the probability. So down here on the Calaveras Fault, this is kind of a creeping section. So the probability of having a large quake down here is lower. Same with this part of the Hayward. It's actually a creeping segment of the fault, but it hasn't been creeping enough to account for the stress that's built up since the last big earthquakes. And I'm going to show you how we dig trenches across the faults to learn about the historical or the paleo quakes, the quakes that happened before we had seismometers in the ground measuring them, when there was just maybe a historical record of someone reporting shaking. And okay, and I just want to point out before I forget them, these other faults, like is it the Green Valley Fault? And there's the Concord Green Valley Faults over here, Diablo Thrust Fault, there's Mount Diablo Thrust Fault, and the San Gregorio Fault that's mostly in the ocean. Those have smaller probabilities of large earthquakes happening on those. But remember I said, together, all of these faults are they're all right lateral deformation. So they're all right lateral strike slip faults, not the thrust fault, the other ones. And they're all making up that plate boundary between North America and the Pacific plate. So you're not fully into the Pacific plate until you're out here, maybe on Point Reyes or in Nevada or in the Great Valley. You're definitely on North American plate then. All right. Oh, it's noon. Shucks. Okay, give me a few more minutes, please. I want to show you a few movies and leave you with the movies. Don't worry about the numbers on this. I just want to point out, here are all the faults that listed by name that are in the Bay Area. And the numbers in parentheses are a best estimate at how fast those faults are moving. So the northern segment of the San Andreas, so north of the Bay Area, 24 millimeters per year. That's 2.4 centimeters per year, about that much. 17 centimeters for the peninsula and the Santa Cruz Mountains section of the San Andreas. The Calaveras, 15 millimeters per year. But when you add up all these numbers, all of the slip, then you get the total slip between North America and the Pacific. The San Andreas is most of it. So I would say well over 60%. I don't remember the exact number now, what percentage this comprises, but you add all of these up together, that will give you 100% of the slip. And then you can take the percentage for different faults to find out what kind of contribution those make to the total plate motion. And this just gives you the recurrence interval for the very large earthquakes. So the Concord Fault has not had a very large earthquake in a very long time. The San Andreas sections, the recurrence interval is about every 160 years or every 210 years or 143 years. So if we can determine using carbon dating and the trenching across these faults when different earthquakes happened historically, we can estimate the recurrence interval like this. How often do we get these earthquakes? That doesn't mean we couldn't have 2 magnitude 7 earthquakes a year apart. That could totally happen. This is just an average over many hundreds of years or thousands of years. Okay. This is something that you can do as a job. You can study earthquakes. You can get down into trenches. This is a trench that they're digging with a backhoe. It gets to be like 8 feet deep or something like that. They dig across, and they can be quite long. And they put up supports so that the ground doesn't collapse on you. And you climb down in and you study what evidence is preserved in the soils and in the rock in those trenches. You can make measurements of the rocks on the surface of the earth, how they strike and how they dip, to understand how the rocks deform. It might be a local problem that you're studying, maybe just one small fault, or maybe you're studying the plate boundary. So there are a lot of seismologists that work for the US Geological Survey. Otherwise, you might work in academia, so at a university. But structural geologists do all kinds of jobs. They're needed for geotechnical work to understand building sites, whether they're safe to build and where the faults are so that you don't build on top of a fault. All right, here's a trench showing, so this is just like what I was showing you. Oh, that didn't show it very well. Okay, this is supposed to be sand, a clay layer in pink, and then the black layer is like a carbon bearing unit. So that might be forest fires that killed off some trees and you've got charcoal left, or maybe it's yeah, that's probably a good option. This is what the trench looks like. These are those I can't remember what they're called, the things that separate, keep the trench open so it doesn't collapse on you. You climb down a ladder to get in, and then you climb through those things. But you're literally studying where the fault is. And you, when you get down there, they're tagged, all the locations of where something a feature can be seen, an offset can be seen. Those get flagged, and they get detailed maps made in these trenches. And then they're closed back up because they're not safe to leave open. But this is paleoseismology is what that is. And I see that word does not show up well. That's studying those ancient earthquakes. Okay, just a couple more slides. Hang on. So this is what the San Andreas and at Point Reyes. Here's a picture with Point Reyes off to the west. And here's, I think this is the Bolinas, is that the Bolinas Lagoon and Tamales Bay behind? That's the fault right there that splits. This is Selenian granites out here, and this is Franciscan rocks, metamorphic rocks over here. So Southern Sierra Nevada rocks separated from the others. This is not the original fence. This is a reconstruction, but there's an earthquake trail that you can take at the Point Reyes National Seashore Visitor Center. And you walk along a trail and you can see the landforms like sag ponds and shutter ridges that form along strike-slip faults. And this is a rebuilt offset fence that this offset happened in the 1906 quake. In one earthquake, imagine this, the earth shifted that much at this place. That's probably 12 feet or something like that. That'd knock you on your butt for sure. Okay. That Point Reyes is right here. That was about a 12-foot offset. I wanted to just point in Northern California, there was a 25-foot offset all along that segment of the San Andreas. This sort of maps out based on the bar height, like how much offset there was. In the 1906 quake, there was a lot of energy released, a lot of stress released in that quake. And there was a huge slips along the fault there. This is just another way of plotting it up, but this is in meters instead. So that says the same thing. This is 25 feet or a little more than 8 meters, almost 9 meters. Okay. There's a law in California. It wasn't created until 1972. It's called the Alquist-Priolo Earthquake Fault Zoning Act. And this act governs all of these faults where you see these yellow boxes. It governs everywhere that there is an active fault. And so where we have evidence that there's been like a historical earthquake or an earthquake that we've recorded recently. Anywhere that is true, there's a zone at least 50 feet wide around the earthquake, around the fault where you can't build. 50 feet doesn't seem like a lot to me, honestly, but I'm going to show you on Tuesday evidence for why not building on the fault is a good idea, because the shaking along the trace of the fault, like where the line of the earth where the fault goes, is more likely to shake more vigorously than elsewhere. So that's one reason this was created, to make sure that people weren't building in some of the most dangerous parts. Okay, this says the same thing that we've been talking about. Everywhere that's red has the potential for really vigorous shaking during a large earthquake. So the San Andreas fault stands out really well. But the Hayward and Rogers Creek faults are there. The Garlock fault is there. The East California shear zone is there. There's potential, a lot of shaking. Actually, last year, I was interviewed on, it was Channel 5 Evening News, interviewed about the earthquake on the Eastern California shear zone that happened, because it was a pretty big quake. Okay, just a few movies and then I'm going to let you go. This is going to show you the motion of the Pacific plate versus North American plate over time. This line represents a spreading ridge. This is the Pacific plate. And the plate that just disappeared underneath North America was called the Farallon plate. So this plate gets subducted, and that's what forms the Sierra Nevada and the Franciscan metamorphic rocks. And all that's left today of the Farallon plate is this little bit of Juan de Fuca plate and the little bit of Cocos plate that is subducting still beneath Mexico and Central America. The Pacific plate is over here still, moving to the northwest. I'll play this one more time. So the spreading ridge moves, it's moving closer to the continent, and it's actually going to be subducted. And as soon as that plate boundary, as soon as that ridge hits North America, that's when the San Andreas fault. One more time, because around 30 million years, that's when this mid-ocean ridge intersects the continent, and that's when the San Andreas fault starts to form, right there. Okay. Here's a closer up look. There goes the Farallon plate. There's the subduction, there's the trench. And here's the San Andreas growing, and it's going to get longer. The Farallon keeps subducting to the north and to the south of us, and then the San Andreas fault grows longer and longer over that time, starting around 30 million years. Right about here is the beginning of the San Andreas, and then it grows longer to the north as the subduction continues to the north. And then we have this whole segment. So this is showing, the other thing this is showing is Baja California, and the LA side, the west side of California, shifts to the north. Just look for that this time. And then I'm going to move to the next one. Here goes the San Andreas, and now Baja and LA are shifting to the north to give us our current geography. This is a slightly different look. This shows you what might happen in the future. Remember I said the Eastern California shear zone might become important? This is what I was talking about. So this is the San Andreas. The Eastern California shear zone goes up behind the Sierra Nevada. That's what's going to happen here. So it's the spreading ridge that's behind, in the Gulf of California, behind Baja, grows and moves to the north. And it starts opening up the Basin and Range province as a small ocean. So this might end up being an ocean eventually, and California could end up being an island off in the Pacific Ocean over geologic time. This configuration is 10 million years into the future. Okay, this is the last one. This is showing the Pacific plate. All right, there it goes. The Farallon plate is gone. We're just developing the San Andreas here. You're seeing a piece of crust with San Francisco on it, a Santa Barbara terrain here, and San Diego and LA here. As the San Andreas grows, it's pulling these, San Francisco and LA and Santa Barbara is rotating and moving to the north. And Baja's coming along with it. So this is showing you what we can tell from reconstructing the faults, like the Garlock fault that crosses California down there. Okay. And then it shows sea level rise to give our current coastline. Are there any questions about those videos? I'm sorry that took so long, but we're still within our official class period. Any questions about what I've shown you so far today? Everyone's being real quiet today.
Will the
right now?
Yeah.
Thank you so much, though.
Go ahead, somebody.
will the
San Andreas Fault keep getting longer as the Farallon plate keeps subducting, or like is this the longest it'll get before it shifts to the California shear zone?
Right. Okay. So let's see which one is best. Is it this one? No. I gotta go up to. I need the right map. This one. Okay. Yes. The San Andreas intersects the subduction, like it joins the Juan de Fuca and the Pacific and the North American plate right there.
Mhm.
So as the subduction continues and as we subduct that last bit of Juan de Fuca plate, yeah, the San Andreas is going to get longer. And it's going to keep, it's as it gets longer, it's also going to keep shifting in a right lateral sense, meaning all of the earth, the crust that's to the west on the ocean side of the fault is going to keep moving to the north. And Baja is going to keep separating from mainland Mexico. So this spreading will continue. The transform fault will get longer. And then what one of the last movies showed you, that the plate boundary is going to shift to behind the Sierra Nevada and toward the Basin and Range. Does that answer your question?
Why does it shift from the San Andreas to?
Because of the plate stresses and the direction of the plate stresses. So we know the Pacific plate is moving to the northwest at a certain rate, and that the North American plate is moving kind of westward, but at a slower rate. We have the San Andreas that's moving in a right lateral sense about, 2 centimeters a year. And then we've got the plate boundary still opening up at a different rate behind Baja. So all of those taken together, they kind of create a complicated structural problem you've got to solve. Like, where are the stresses going to be and which direction are the different vectors going to be pointing? So what this is telling me is like the future prediction that it's going to move this direction is telling me that this spreading is moving to the north, or it has already started moving to the north, that we already see earthquake seismicity in that area along the Eastern California shear zone. So it's already active. And there's a weak place in the crust right there. And it also forms the west side of the Basin and Range. So there's spreading happening there too. Right now it's just in the crust, but it's eventually gonna connect with this spreading ridge, the spreading center in the Gulf of California, and open up an ocean in here.
Okay.
So it has to do with the direction and the magnitude of the tectonic plate motions that are involved in all of this. I hope that's good enough for an answer. Was there another question out there? Okay, I thought somebody else had one. That's all right. You're going to have lots of time to ask more questions. Tuesday and Thursday, you can come tomorrow from 11 to 12. I'll be around and happy to work on questions about the lecture or the lab, either 5A or 5B. That's it for today. So Ashanti, I think you wanted to stay and ask some questions about Google Earth. Anyone else who wants to stick around and ask those, please stick around. And see you Tuesday. Have a good weekend.
Thank you.
Thank you.
You're welcome. See ya.
So I have to share my screen with you?
Yeah, let me stop sharing here so that you can. Okay, it's all yours.
Actually, I do have a real quick question just to ask.
Sure, go for it.
That's okay.
Yep.
On Tuesday, you said that the lab was due on October 9th. Then on iLearn, it says it's due on October 2nd. So I was just hoping to get a little bit of a confirmation on that.
Sorry, I didn't realize there was a conflict. The 9th is correct.
9th? Okay.
Yeah, I'll go and fix that.
Okay, I was just trying to make sure. So
The
5
9th is
a.m.
left, but it's also going to be your earthquake lab is going to be due around the same time. So I'm fixing that date as we speak. So it
Okay.
says the 9th. You don't have to worry. 9th. Okay. It says it's corrected.
Okay, thank you. And then sorry.
It's all right. Gather your thoughts.
Yeah, sorry. Never mind. I guess I didn't have it.
Well, if you think of it, you can write it down and save it for next time.
Okay. Thank you.
Sure. See ya.
Okay, so I figured out how to get the app downloaded.
Awesome. Have
But I
you
have a
installed
question
it?
about the lab.
Okay.
Can you see my screen, right?
No, I cannot. Try again.
Can you see it now?
Yes, I can see it now.
Okay, so here's the.
You've got Mount Hood, good. You've got the topography in there, that's great. So you've got it working, that's fantastic.
Wait 1 second. I'm not sure how to get it back up here on the side. But I was a little confused from this question. It says, 1 second. What is visible in the Google image where the topographic map contour lines are brown rather than blue?
Aha. So on Mount Hood, for example, you've got, there should be blue, it's kind of bluish lines on top of the glaciers. So it turns to a blue contour line. Turns to blue contour line over the glaciers that you see on top of the mountain.
Yes.
Or on the sides near the top. And then areas where it's brown is simply, that's not where, there's no ice there. It's earth. So you're looking at rocks and soil. That's all.
Oh, I'll see. 1 second. Like, what do you mean? Like, there's no ice, it's just.
So the glaciers are just in like patches that you can see that are like, they're labeled and you can see they kind of like fill some bowl-shaped areas on the side of the volcano. And then in other places, like where the ridges are rocky. And so there's no glacier there. The ice hasn't stuck around on the ridges. It's just so the brown areas, the brown contours are on areas where it's just rocks and soil. Does that make sense?
Yes.
Okay, good.
And 1 second. I'm taking notes. Okay, so that's my question for that one. And this one, so you're just asking us to basically tell the difference of them?
Yeah, all it is asking is like, look at the map and see that there are blue contours on the glaciers where there are glaciers and brown contours where there's rock. That's all.
Okay, thank you.
Okay,
That's all my question.
that's it?
Yes.
Oh, well,
Wait.
that was easy.
Yeah.
Okay, well, you know, you're welcome to send me, send me a message, email me, do a Q&A or some forum post. And if you've got more questions about this lab, just let me know, okay? I mean,
Yes.
we went over some of this, so maybe watching the beginning of this recording again would help you to finish that lab.
And I want to make it clear. So you said the blue contours are glaciers.
That's where the glaciers are, right?
And
So
the brown are rocks.
rocks and soil, yeah.
Thank you.
Mm-hmm.
That's it.
Okay, great. Well, have a good weekend.
You too.
Sure. Thanks.
I'm trying to exit. It's okay.
It's okay. It's hard to find the button sometimes.
You have a nice day.
You too.